Hi, we're Martin, Fiona, and Hannah, and we're presenting our final presentation on scooping for 64210 Fall 2022 Robotic Manipulation. As with DexAI Robotics Alfred, which we talked about in class, they use a trajectory optimization scooping technique. However, besides some niche applications of scooping in industry, there's little academic work in scooping. Best we could find was scooping with a flat spatula off of a flat surface, whereas we're going to be exploring scooping with a convex tool. And based off of all of the previous research, as well as some previous conversations with Russ, we decided to try and pursue our pre-compute then choose approach, where we pre-compute appropriate trajectories for different bin states, such as empty, half full, and full, then use perception to try and determine which trajectory to select. And so this is the direction that we eventually hope to take this project, although we did not quite finish pursuing the perception selection process. The first part of our project was setting up the scooping environment. It's pretty similar to the bin picking setup. The main difference with our EWA arm setup is that there's a measuring cup that we have welded onto the end of the EWA. In addition, we are using spheres instead of bricks for collision geometry. And this is because they're way easier to simulate, and we were running into significant issues with our simulation speed, even after we updated to use the SAP contact solver, which is faster than the default MeshCat contact solver. And actually, the simulation speed constraint becomes a pretty strong constraint for how we thought about the granularity of our poses in the future.
We pursued two approaches in parallel, and the first one was our geometric scooping. This is adapted from the Robot Painter notebook that we saw in class, and the key idea here is we're using simple geometries to plan the motion of scooping from one bin and pouring into the other. So for the scoop trajectory, we started with a circle, but it was really hard to balance getting deep into the bin and also being able to turn the scoop upright at the end. So we ended up using an ellipse to have more control over both the width and depth of the scoop. For the pouring, this motion was less constrained since we're starting out of the bin and then moving the objects in, so we could still use a circular path.
For our other approach, we went for a teleop record. And so the idea was if we could scoop successfully using teleop, we can save those trajectories and use them back later. So this took us 2 steps, 1 recording and then 2 playback. For recording, it was pretty straightforward because we tried to set up a good interface for us to record with. So it was pretty much teleop the robot as you would usually. And then when you're done, you would press the save poses button and it would save it all to file. From the user standpoint, pretty easy. But behind the scenes, we had to put in quite a lot to make it happen. And the way that we had the poses saved was we used a file representation of a file with basically 1 pose for each line, where each pose is represented by a 6 tuple. You have rotation for 3 of the numbers and then XYZ for the other. They're not perfect descriptors, but they work when you're trying to just get from 1 pose to the other for a long list of poses.
So teleop record playback. The main components to using the teleop record for future automatic playback are in cleaning up the teleop path, reading the files that they're stored in, and actually moving the EWA arm based on the information that we read. So a single trajectory file will usually hold an ordered list of desired poses, and there's often more than a few unnecessary positions within this file, just because of the nature of teleop. And so some manual cleaning is sometimes desired. In addition, deleting and adjusting poses can sometimes help with resolving issues from the EWA getting stuck or having joints that are fully extended. And we parse these cleaned files to create paths based on the movements between poses rather than the positions themselves. And then the EWA can then be directed to execute these movements.
Now we'll talk a little bit more about our results. So here we have a video of a full scooping and pouring path with our 50 simulated spheres. So we sped this video up by 5 times because, as you can see, there's a big slowdown when the scoop starts interacting with the spheres. And with this trajectory, we also tend to have to push some spheres out of the bin, but we can reliably pick up 3 spheres every time. After the scoop, we have an intermediate frame to make sure the scoop stays upright so we don't drop the spheres we just picked up. And then finally, we move on to pouring into the other bin. Both approaches yielded successful scooping and pouring results. While the geometric approach created relatively smooth trajectories, it proved difficult to navigate the bin environment and plan what geometric shapes would work best. The teleop approach creates much more flexibility and can quickly plan trajectories to new situations, but may be a little bit less smooth.
So some of the challenges along the way and lessons we learned. We found that even though this is a robotics class, a lot of the stuff we did to help us out were actually just good software development sort of deal. And some future work is that we settled on our scooper early on, but it's actually not the best scooper for scooping. The walls are actually pretty high on the scooper, so it's tough to get it to go into a bin full of spheres. And also, we didn't get to automatically choose the trajectories through perception. There's also room for trajectory optimization. The trajectories you get are ultimately as good as the trajectories that you can teleop yourself. Part of that is probably making a cost function for scoops. Not sure if this is something for Drake or something for users of Drake. Speeding up that simulation should make things better. But yeah, that's our scooping projects. So, it was tough. We learned a lot. Thanks for watching.